Morning, everybody. Thank you for joining us for this webinar on advancing digitalization and composite technologies for safer, more sustainable aviation. I will start in 1 minute. I will just give some time for people to join, and then we can start. So, for the purpose of saving time and avoiding getting too late, we will slowly start. And my colleague Martina is going to share in the chat how you can interact with our session. Once again, thank you for joining us. Let me welcome you for our webinar. I am Giulia Barbagelata from STAM. I'm the dissemination leader for the DEMOQUAS Project. The reason why I wanted to start sharp on time is because our agenda, as you can see, is quite packed for this session. There are 3 projects that are going to be presented today, and for each project we are going to have approximately 10 to 15 minutes presentation, which, as you can understand, if you are familiar with the research project, is quite tough to do. And then we are going to have time at the end for the question. The reason why we are going to have this session, which we hope is going to be the first of at least 2 to 3 other sessions, is because the 3 projects that we are going to discuss today have common topics, and although they are at different stages of their life, let's say, they are tackling similar topics. When we started this discussion a few months ago, we agreed together what was the main topic that we were going to discuss during this session today. And again, let's hope that this is going to be the starting point of a cooperation. Of course, one of the projects is coming to an end, but there are always new projects that are starting and facing the challenges that we are. Also, it's very important, not only for the purpose of research, but also for the European Commission that is funding our project, to see that we are working together in order to share results and build upon each other work. So the first project that is going to be presented today is going to be the DEMOQUAS Project, which is about designing, manufacturing, and operating quantification of uncertainty to increase aviation safety. The presenter is going to be Vasilis Gkoutzamanis, which is the Vice Project Coordinator from Aristotle University. It's going to be followed by GENEX project, which is about the new end-to-end digital framework for optimized manufacturing and maintenance of next generation aircraft composite structures. It's going to be presented by Carlos Mayor Turon, who is as well the project coordinator, and he's working at Instituto Tecnológico de Aragón. While the last project that is going to be presented is TOSCA project, which is about manufacturing processes and digital tools for more sustainable composite air structures. It's going to be presented by Christian Etzinger, who is the project coordinator and works for TOSCA project and works in ProFactor. And then we are going to have a session for questions. Of course, given the tight nature of today, the session is going to be 10 minutes, but fear not that your question is going to be lost. If we don't have time to answer today, we are going to answer via email. And you can write your question in the dedicated section in named Q&A, or you can write them in the chat. And after the session, you will receive the link of the registration for today's session. So again, if you have any questions, write them down. And without further ado, I will leave the floor to Vasilis Gkoutzamanis for the DEMOQUAS presentation. Thank you, Vasilis. The floor is yours.
Thank you, Giulia. Let me share my screen. Okay, let me go full screen. Can you see it?
Perfect, thank you.
Excellent. So, thank you, Giulia, for the introduction, and thanks to everyone attending this webinar. So my name is Vasilis Gkoutzamanis. I'm a researcher and a lecturer at the Department of Mechanical Engineering at the Aristotle University of Thessaloniki in Greece. And together with Professor Anestis Kalfas, we are coordinating project DEMOQUAS. Before I start, I would like to also thank my co-speakers, Carlos and Christian, for this webinar we're about to have, and also the teams that organized this meeting. In particular, Julia, Vasiliki, Martina, and apologies if I'm forgetting someone. And also I have to thank, we have to thank the European Commission for funding this project. So, presentation outline. First of all, I will give a short introduction to our consortium and advisory board members. Then I will talk a little bit about the challenges and the objectives of this project, as well as the solution that's bringing. Then a high-level methodological approach, given the limited time that we have. Also, a reference on the application activities and the test cases. Lastly, the expected impact that our project will have. So this is the consortium of DEMOQUAS. It comprises from an interdisciplinary mix of partners spanning academic, small, medium enterprises, and industrial partners. So regarding academia, we are partnering with Imperial College London and TU Delft. Also, regarding SMEs, in an alphabetical order, we are partnering with Advice Data, B&T Composites, and Digitalization Aviation in Greece, ICOMAT in the UK, Limat Scientific in Switzerland, and STAM Italy. Also, we have our OEMs, which are the Rolls-Royce and Safran. And also, one of our partners, which is the Digitalization Aviation, the pilot training school, operates a small airport on the northern part of Greece. So there is also an airport case in the consortium. In addition, we have some advisory board members on board for which we are grateful, and they come from the NASA Langley Research Center, the Cryostar, and the Hellenic Civil Aviation Authorities. But as we mentioned at the beginning, DEMOQUAS means designing, manufacturing, and operating quantification of uncertainties to increase aviation safety. This means that, in essence, this project tries to see what are the links over several phases of the life cycle of how uncertainties can propagate, and what can we do to further increase aviation safety, and especially when new technologies come into play. In brief, the project's main objectives are to perform detailed characterization of uncertainties for systems and subsystems for a turboprop-based aircraft based on a hybridized liquid hydrogen and SAF configuration. Secondly, to implement and extend uncertainty quantification methods across scales, fidelities, and life cycle phases. Thirdly, to deliver an as open as possible UQ framework to increase aviation safety, addressing both novel technology design processes as well as the human factor. And fourth, to verify and validate these methods up to TRL 5 for specific components. Obviously, the fifth objective has to do with the synergies, and this webinar today is part of our main objective 5. Maybe these objectives do not say a lot so far to you, so I will try to delve a bit deeper of what we mean by its objective. And first of all, I would like to highlight how the project is linked with the main title of the webinar. And this is, on one hand, the more sustainable aviation goals. So we are working on disruptive aviation technologies. The main scope of the project comes with hybridization and electrification, as well as on the use of alternative fuels. This is why you see these words highlighted. And on the other hand, some of the test cases work on composite structures, and these comprise from engine components as well as on the fuel tanks. So essentially, this creates the challenge. So the challenge is new components, new technologies, which brings forward design uncertainties, which put safety at, let's say, a risk when it's a new technology, and we need to delve deeper and provide evidence-based quantification of the safety factors and the safety margins. On the other hand, whenever we talk about new propulsion systems, for example, distributed propulsion, when we have multiple propulsions on board, the components of the system can increase. This may raise some issues with respect to failure cases on the systems level, and we need to be able to address those. So in a way, the safety factors which have been applied through all these years in aviation rely on old assumptions and may need to work further to cover all new risks. In addition, we need to make the confidence in the error margins more robust. I will explain a bit further of what does this means as my presentation evolves. So we have a solution. The solution is a digital tools which are targeting to, at the very end, make aviation even more safe. And we propose to deliver an uncertainty quantification framework that will provide with all those tools being used either for aircraft design or for engine design and performance quantification and all the other subsystems with the capability to become UQ enhanced. Our ambition is to provide guidelines. So at the very end, we would like to support virtual certification. For example, we would like to provide to the regulators with tools that would increase confidence in whenever a new technology needs to be certified. So in a way, what would be the research question out of this project is how could we link together information, including its uncertainty, emerging from all stages of a new product's life cycle. As a note, we imply with the word product not only to a single component, but this can either be a subsystem or a component or even a system, an entire system. Okay. So what do we want to do first? We want to identify sources of uncertainty spanning throughout the different models that we are developing for the various use cases. The sources of uncertainty, maybe some of you are already familiar with, can be classified into the aleatoric and epistemic type of uncertainty. Aleatoric means inherent uncertainty, and it's kind of hard to be reduced and identified, and we want to make our models more robust so that we can address this part of uncertainties. On the other hand, epistemic uncertainties are those that come with due to the lack of knowledge, and as a project matures and goes up the maturity ladder, these epistemic uncertainties are reduced because we gain more knowledge. To be more practical and explain what I mean with that, for example, during the design process, we may have some uncertainties associated with the material properties or associated with the boundary conditions of the model. If the model is of more high fidelity, more detailed, these uncertainties may come with, for example, the turbulence model. If we move up one step, move towards the manufacturing process, then it comes with tolerances and manufacturing defects. If we move further to the life cycle and we have a component manufactured and tested, we then see operational uncertainties, and these can be, for example, uncertainties linked with the environment, weather conditions, maybe with the measuring instrumentation sensors, for example, and also even the human factor, which is, for example, the pilot's performance. So in a sense, we want to create pipelines, it's computational pipelines and or processing pipelines, in order to investigate how these things, what is important, what is less important, and how do these uncertainties move out throughout these processes. And at the very end, to provide concrete evidence-based numbers of how important is one parameter with respect to a new technology. So in a bit, as I said, it's a high level description here, methodological approach. We are almost halfway through our project duration. We are currently in month 17. So what we have done so far is we have identified our project requirements and assumptions. Secondly, we have further developed and integrated different models and created the actual modeling pipelines. And when I refer to modeling pipelines, these can be either, let's say, systems connected together. An example is an engine an engine working together with a fuel circuit. But as I said previously, we want to evaluate uncertainties at multiple levels of fidelity. This means what do we do if we want to combine models that do not analyze each part at the same level? For example, we have a low fidelity, so a systems model, and we want to couple it with some higher fidelity analysis like computational fluid dynamics model or a finite element FEM modeling analysis. So this was the second major part during the first months of work, to establish our pipelines. And thirdly, to develop our methods and try to let's say, implement a common uncertainty quantification approach for the different models. Indicatively here, I have included the propagation across scales, data fusion when we have the different types of data, heterogeneous data as we call it, and reliability formulations when we have scarce data. And what we are currently focusing on is the development of the test cases. So manufacturing activities are also ongoing. And the main goal is to collect the different data coming from the different processes. In very brief, I understand that this slide may be a bit, let's say, too dense to follow, but we make a classification between application activities and test cases. Application activities include all modeling approaches, whereas test cases include those particular cases where we will have actual testing data, manufacturing data, and even data from operations. So we start from the system of systems. For example, this could be the aircraft system, moving on to systems from a technology's perspective, and this could be our engine, our propulsion system, and also the subsystems, which are the components from storage to burn. A tank where the fuel is stored, including the conditioning of the fuel, for example, the heat exchangers, as well as the combustion of the fluid in the engine. But there is another perspective in this project. As you can see, bottom left side, the system's human factor. We assume that the human factor acts as a system, and we try to quantify the interdependencies that may have an impact on the pilot's performance during operations. And we want to see how we can couple that with an uncertainty quantification method. Some examples of the test cases. These are not all the test cases, but I have chosen indicatively some to provide some more words on each one of those. And you can see here, this is also how our work is linked with the composite structure development. We want to couple the uncertainty quantification modeling with the CAM processes, so computer-aided manufacturing processes, and the eventual processes of manufacturing, so rapid tow shearing coming from Micromat, or processes like the filament winding from our partner in Greece, B&T Composites, and also be able to create a pipeline during manufacturing and measuring process. A second subsystem comes with the cold plates, which are used for the power electronics. And the perspective of this use case is to perform topological optimization, provide topologically optimized shapes, which proceed further to the manufacturing processes and testing activities. So this activity also contributes to the verification validation assessment, and this is directly involved with certification processes and digital certification principles that also EASA has. What you're seeing here is a cold plate example and a use case performed by Rolls-Royce on the cold plate for the heat exchanger of an of power electronics. And then moving on to the right-hand side of the slide, at systems level and technologies, we are working on the engine performance quantification. The risk here comes with the, not the risk actually, but we want to be clear on how an engine degrades during its operation and various cycles of operation. So we want to be sure and be even further reduce any uncertainties that would characterize the remaining useful life of this component. As I told you earlier, again at the systems level, but from a human factor perspective, we are developing a model, a machine learning based model, so using the Bayesian networks. And we want to quantify the pilot's performance. So we want to see how the different dependencies spanning from environmental factors, the pilot's competencies, how the human factors and the organizational factors of training may overall lead to the pilot's performance. And we want to see further how these methods can improve this part. Yeah, I see that my time is almost there, so I will be very brief. Failure modes is with respect to the system's redundancy. So we want to see that the propulsion system operates even if a component for some reason may malfunction or stops to operate. So we want throughout the whole mission that we have redundancy in each of the systems and subsystems. As a closure, we expect that we will contribute towards EU goal of maintaining the highest level of transport safety for EU citizens. We want to quantify and continuously update the safety margins and provide evidence-based characteristics. And at the very end, we want to establish a unified uncertainty quantification framework for the three, let's say, safety pillars: technologies, human factors, and regulations. So I would like to thank you for your attention, and I would be happy to discuss during our Q&A question and even further if you want through my contact details. So thanks a lot.
Thank you, Vasilis, also for being considerate for time. Again, please write your question if you have, either in the chat or in the Q&A, and then I will quickly move on to the next presentation about GENEX, who will be done by Carlos. Thank you, Carlos. The floor is yours.
Thank you, Julia. Thank you, Julia, and all, first of all, for organizing this event. I'm going to share my presentation. Let me. Okay, I think you can see it now, full screen. Right?
Yes. Now, yes.
Okay, so good morning, everyone. My name is Carlos Mayor. I'm a PhD in mechanical engineering working at ITA, the Aragon Institute of Technology in Zaragoza, in Spain. And today I'm going to be talking to you about the GENEX project. I will talk about our approach for manufacturing, maintaining, maintenance, and structural health monitoring and repair for the next generation of aircraft parts, aircraft composite structures. So I'm going to start off with a little bit of introduction. Some figures about the GENEX project. It started in September 2022 and it lasted for 3.5 years. So it will be finished next February. So we are almost there. And we had a budget of 5.7 million euros, and we have many different partners all across Europe. As I said, this project is coordinated by us, by ITA, and we have a really great consortium. We also have some technology centers such as DLR or IMEN, CDTech. We have some universities across Europe and some end users such as GMI or Arnova. And yeah, this picture here is from a mid-project meeting we had in DLR facilities. They also have there a hangar with some airplanes, and yeah, I really like it. This is why I wanted to share it with you. So what about the objectives? Those were really aligned to the topic, to the call from the European Union. And the main one is to develop a digital twin framework for optimizing manufacturing, health and usage, and monitoring and maintenance and repair of the next generation of composite structures for aircraft composite parts. So this is our main focus from the very beginning, and we have some other specific objectives. And the first one has to do with using more eco-efficient materials and also make more eco-efficient the processes of manufacturing these advanced composite structures. The second one has to do with monitoring the parts, how they work in use and how they may be damaged, or they may have an impact or a delamination or whatever. And for that, we develop physics-based simulations and sensor systems. I will be talking to you about a bit later in my presentation. The third specific objective and also pillar of our project is to introduce in this really nowadays manual repair process of this kind of parts, to introduce some digital methods, digital assistance in order to help the operator to make the repair more accurately. And these are the very basic 3 pillars, and we have an additional one which is kind of transversal because it tries to interconnect everything together here. So we wanted to create a multidisciplinary platform, a digital twin platform, able to gather information throughout the whole life cycle of this product, covering from manufacturing, usage, and also repair, so that we are able to create, I would say, an ID of the part in order to have a log of the whole life cycle. And just as we saw in our last presentation, why we are here today. So the GENEX project is here obviously because, as I said, we are advancing in digitalization. As I mentioned, for instance, provided augmented reality tools for repair. We are talking about composite parts, composite technologies. We want to make them safer because we are going to develop technologies that are able to control the health of the component. And we are also talking about sustainability, as we are using eco-friendly materials and more eco-friendly manufacturing processes, and for aviation. So we are using aircraft composite as demo cases. So this is clear, fairly clear why we are here together with DEMOQUAS and TOSCA, GENEX here sharing our developments. So the concept. I mentioned the 3 main, the 3 specific objectives, and for each of them, we envision 3 main, let's say, digital twins. The first one has to do with everything related to manufacturing. The second one, product usage, structural health monitoring. So yeah, I was saying that we envision a solution with these 3 main digital twins that are related to the 3 main specific objectives. And the first one has to do with manufacturing. The second one, product usage, structural health monitoring. And the third one, maintenance, repair, overhaul operations. And as I said, there is also a transversal one, which is we wanted to create a digital platform that connects everything together, and it's cognitive one, so we can take action in here. So that was our proposal. And now, as I said, we are close to the end of the project. So we develop many of the technologies. I am going to briefly describe those. So the first digital twin, things related to manufacturing, we develop 3R resin pre-impregnated tapes. So we are using a recyclable resin here, embedding carbon fibers. This is done by CDTech, and we manufacturing these tapes, and we are using those by, I mean, in this case, using an automated tape layering process. We optimize the process windows, the different parameters here, laser power, and so on and so forth, in order to be able to manufacture our demo case properly. You can see here in this video on the right that how we are manufacturing in this case one of our demo cases, which is a spar of an horizontal stabilizer of an aircraft, of an Airbus. And this is how we are manufacturing this kind of C shape of this spar, and we are curing it with laser. And in parallel with this head, we also develop a terahertz monitoring head, which is able to measure the degree of curing and the degree of crystallization as we are applying these tapes in the final part. And also, we work in our project in developing reduced order models in order to predict the degree of curing beforehand. So basically, this is a summary of what we develop in our project. Nowadays, we are actually manufacturing these demos, so we are in the demonstration stage of the projects, in the very last one, and we will test soon these parts in the next, according to the next developments, which are here. So this is the second one, so product usage, how our product, in this case, the demo case spar, behaves over time when it is under real usage. And in the very core of these technologies lies ultrasonic guided waves simulations, as you can see here in this animation. And basically what we are doing is we are monitoring our structure. We are controlling a baseline where the component is pristine, and we are able to detect, thanks to some piezoelectric sensors that are optimally arranged in this part, we can detect if some event happened. So if we have an impact, or if we may have a delamination or whatever. And we developed this technology with tons of simulations and also a lot of actual mechanical tests, all of them monitor using these sensors that were embedded in our parts in the previous manufacturing process that I presented to you. And then we have an arrangement of sensors. So we are able to receive the information of these sensors, and we collect it in a wireless sensor node, which is developed by CSEM. This is an ad hoc technology that we develop in this project, especially designed in order to send the information to the digital twin that is able to run, in this case, the machine learning algorithms that analyze that signal from the sensors, and they are able to provide an answer of we had an impact of, or if we have a delamination, where is located and how big it is. And thanks to this information, we are able to trigger our next part of this health assessment, which has to do with fracture and fatigue analysis. This was done by ITA. We are experts on this, and we envision a really comprehensive set of simulations in order to cover our parametric space, together with a really huge characterization of materials of the 3R resin, as I mentioned. And we were able to embed in reduced order models those fracture and fatigue predictions. So we take information from the initial delamination, and we can estimate how this delamination area will grow over time according to the usage of the real component. So in the end, we are able to predict the remaining useful life. Okay, so I'm talking about the third one. Here we develop, as I said, many tools regarding digitalization of maintenance, repair, and overhaul of these kind of structures. The first one has to do with virtual assisting the scarfing process. So the scarfing process, very briefly, is basically to remove some of these stacking layers of the composite where we have to perform a repair. We may have there a delamination or an impact or whatever, and we need to remove this This is done very manually nowadays, but thanks to the developments of DLR colleagues, we are able to use augmented reality in order to help the operator to perform this operation more accurately. Then, in the second one, we also thought that it was interesting to work on the cleaning. And we may have here dust or oil or some other things that may interfere in the patch repair. And for that, we develop a lift system, which is laser-based, where we are able to detect and also to remove this dust or whatever we may have here. Then this third part, this is what we develop in collaboration with GMI colleagues, and we are using here an system they have there in order to apply a heat flux to some blankets that are put on top of the patch repair in order to cure it once it is scarred and is ready for the repair. And we are controlling here temperature using a limited amount of thermocouples, but we together develop a reduced order model in order to estimate the full field of the heat transfer that we have here. So we are providing tools that help us to control the process in a better way. And lastly, we also develop within this block some crack stopping technologies that we are able to put them in the interface with the patch and the actual component in order to be able to stop those cracks in the event may occur again. So basically, those are the technologies in this third pillar, as I mentioned. And lastly, this is the transversal one. So this is the platform that we are nowadays still finishing. And this is the digital platform that needs to communicate with all of the other pillars. So it takes information from the actual sensors during manufacturing. It is also in charge of running the algorithms that I described regarding structural health monitoring and fracture prediction, and also take care of the digital twin of the repair that I just presented to you. So this is kind of the end goal that we aim in the very beginning of the project. Okay, so just to quickly recap, I want to talk about how transfer project, so transfer GENEX technologies are transferred to the industry. So we had some industrial partners, Arnova manufacturers, Ziegler and GMI experts in repair. And as you can see, they are benefiting from those advancements. And we also got some really important people here to the advisory board from the Lufthansa Technical Training in Germany and also from Tarmac Aerosafe here in Spain. They really help us throughout our project to be very focused, very close to the industry, very aligned to the real needs. So yeah, we consider this a really important part. And together with them, we are still these days preparing guidelines for maintenance repair and aiming composite repair certification, always taking care of life cost and also life cycle analysis. And just to conclude, I want to highlight again that we were developing this whole project, always thinking about the society in general as a main beneficiary, as we are more these days concerned about the eco-efficient materials and processes. So yeah, I just wanted to close with this point. Okay, so I think this is all from my side. Sorry for the interruption. I got some connection problems, and these are my details, and this is our webpage. So please feel free to contact me if you want to talk about some of the technologies involved here, or if you have any other question. Thank you so much.
Thank you, Carlos. Yes, if there are questions, please write them down. And without further ado, I will leave the floor to Christian so we can enjoy this presentation as well. Thank you, Christian.
Thank you. I'll start straight ahead by sharing my screen. Can you please confirm that you can see the presentation?
Not yet.
Okay. Wait a second. Okay. Is it visible now?
Yes, now it
Okay.
is. Thank you.
Okay, so perfect. So welcome. My name is Christian Eitzinger. I'm working at the Research Center Profactor in Austria, and I'm coordinating a project called TOSCA. The idea of the project TOSCA is to increase the sustainability of composite aerostructures. And we are starting essentially from a new type of material for which we want to do several developments. The background for the project is about parts that may be relevant in future aerospace, especially electrical vertical takeoff and landing applications. And the parts that we are looking at will be scaled down versions of these future parts, but they will have the main features that we expect to be present in these future aerostructures. And as a particular focus of the project, we are dealing with sustainability, and that also gives the connection to the webinar that we are now having. In our project, sustainability is not only a materials topic. Clearly, materials are important, but if you substantially change the materials that you are using, this will have significant impact on the processes, not only during manufacturing, but along the whole life cycle. And in the project, we're also looking at how digitalization can improve the processes and optimize the reuse of parts at the end of their life. In order to do that, we are dealing with three different topics. The first one is on the material side. Epoxy vitrimer resins have already been developed. They combine the advantages of currently used thermoset resins in terms of mechanical strength and durability, and on the other hand, the advantages of thermoplastic materials that are more easy to recycle. And we want to make use of both of these advantages and develop processes that use these vitrimer resins so that they are really suitable for the manufacturing of future aerostructures. The processes that we are looking at include the main manufacturing processes such as layup and welding, but also processes that might be relevant in the future during the life cycle of the parts, especially repair processes. And along this whole life cycle, the automated documentation of the parts as they are manufactured and as they are used, that's the main part for digitalization that we are looking at. Just a brief overview of the production process. The standard manufacturing process ends basically here where the parts are finished. We are following a somewhat, let's say, standard approach, starting with layup, where you create the stack of material. We are using pre-preg material in our project. We will look at ways how to integrate structural health monitoring during the layup. There will be some curing stage, and there will be an additional welding stage to join the cured parts. This is different from current thermoset resins because thermoset resins are obviously not suitable for welding, but the new vitrimer resins enable us to do that. And once the part enters into its life, we are performing structural health monitoring to acquire information about what's happening inside the part. And we are also looking into repair processes. On the one hand, making these processes suitable for the new type of material, but also on how we can acquire digital information about the repair processes, which is a bit tricky because very often these processes are manual. And the backbone for all of this is a digital model of the part. We may call it a digital twin that is collecting information about what has happened to the part during its lifetime. And we can use this model at some stages of the life cycle of the part. Just a quick overview on the main technical achievements. It might be relevant to know that the project has just started. So we started working in January 2025. So we are now in month 9 of the project, which is still in an early stage of this 3-year project. Regarding the Vitrimier resin, or the new type of resin that we want to use for the prepreg material, the main focus is to increase the durability. As you might know, standard prepreg material needs to be stored frozen in a refrigerator at something like -18 degrees. And once it's taken out of the refrigerator, it has to be used within a period of, let's say, 24 hours. And what we would like to achieve is that we don't need to store the material in a refrigerator, and that its durability is much longer than is currently the case for thermoset resins. And one key aspect is that we still need to be able to process the material properly, which requires a certain level of stickiness or tackiness. And we need to make sure that the viscosity of the material is in the range so that it's usable for automated fiber placement, which is the main layup process that we are using in the project. The second aspect is the automated documentation, and we are acquiring two different types of information in our digital twin. The first one is very similar to what we just saw. It's about collecting information coming from structural health monitoring systems and then creating some kind of estimates on how, for example, cracks will propagate and how this will affect the remaining lifetime of the part. So this happens when the parts are in service. The second type of information that we are collecting is quality control information. So if there are certain types of defects, and for example, in an automated fiber placement process, you might find defects such as gaps, overlaps, twisted towels, fastballs, foreign objects. So there's a whole range of different types. And what we would like to investigate is how do these defects impact the remaining margin of safety, so as to decide whether the defect needs to be removed or whether it can stay inside the part. And the idea would be to do this through some kind of simplified finite element calculations that provide then a targeted prediction what will be the effect of a particular defect that we found. And finally, regarding the processes, we've started working on the layup process by designing a specific layup head. Clearly, the mechanical structure is somewhat standard, but there are certain process parameters that need to be taken into account because the type of resin is new. And also, we are looking into integrating sensors for the automated inspection, which then may happen while the layup is taking place. And this will substantially improve the productivity of the process. We are also investigating welding as a process. One of the challenges that we are looking at is the heating systems that are needed, which we will try to solve through carbon fiber filaments or carbon nanotube filaments. And finally, we are also investigating the repair of such composites using digital twins and acquiring information about what has actually happened on the part during the repair. And the technology provided by GMA Aero, who are partner for the repair topic, also allows the creation of some kind of physical twin. What do we expect to get out of the material once it's finished in roughly 2.5 years? On the one hand, we would like to have high quality manufacturing processes for this new type of material. So that will be a prepreg material with Vitrimier resin. And the technologies that we are developing should be applicable for future aerostructures. That is, they should cover the main features that we expect. In terms of long-term impact, one key target is to reduce the recycling, to increase the recycling rate, which is currently, depending on the sources that you ask, around 15%. And we would like to achieve that at least 50% of the parts have the possibility of being recycled in the ways that we are investigating in the project. We would like to increase the production efficiency. This is mainly happening at the layup stage, where we have the integrated inspection, which then removes all the time that is needed for visual inspection. We would like to simplify the repair of composite aerostructures. Currently, for thermoset resin, including the scarfing that we've just seen in the earlier presentation, that takes about 53 hours for typical repair, and we would like to reduce that to about 20 hours through the simplified behavior of the Vitrimier resin. And finally, we would like to reduce the need for any kind of manual documentation along the whole life cycle of the part. So these are the long-term impacts that we hope to get out of the TOSCA project. Currently, as said, we are just in 9 months into the project. We've so far manufactured 2 batches of this new type of pre-preg material. We've tested it. The second batch now shows good results on the different types of processes, layup, welding, and repair. The layup head that we want to implement has been designed, built, and is currently being installed at FIDAMC, who are doing the layup. The inspection sensor that is to be integrated on the layup head is currently under construction and will be finished by the end of this year. And we have also agreed on a data format for the digital twin, which we've made based on, let's say, a standard format that has been proposed by Dassault Systems in their CATIA environment. And we thought that this might be a good basis with a chance of being more widely used in the aerospace industry. And we've set up an initial example of that data structure, and we are now in proceeding to use this for the test parts. Yeah, so that's the list of partners in the project. I will not go through this list due to time that we've got. And that's all I can say about the TOSCA project at that stage, and I'll be open for any kind of questions that you might have. Thank you.
Thank you, Christian. You have been very timely, and I much appreciate that. Thank you to all the presenters. I think it was very interesting and useful. I will move on to the question that we have received. This first question is about Vasilis' presentation. I don't know if you had the chance to see it already, but I will read it briefly. I'm not sure if I missed it, but could you provide information on what platform or tool the uncertainty framework is being developed or planned to be developed?
Yeah, so thank you for your comment. So I would say that, yeah, mainly the tools are, we have some tools either commercially available or in-house tools that we combine, mainly, let's say, following the Python tool. But when it comes to the uncertainty quantification framework, we work with libraries like the ChaosPy and so on. So I hope this answers your question.
Thank you. And then we have a question for TOSCA project, which is digital twins are often seen in relation to digital product component passports. This topic is pushed a lot in the context of sustainability, recycling, and remanufacturing. However, part manufacturers are reluctant to feed their data in such twins or passport. What could be incentives for part manufacturers to use such digital twins / digital product passports?
Yeah, indeed, this is a major issue because the part manufacturers just don't want to share their whole CAD models, which is particularly relevant for composite parts because you would then have to share the whole ply book or the layup on how it's made, and this is very difficult for these partners to do. So at the technical level, there are tools required that allow other actors along the life cycle to selectively access the information without the need to share the whole CAD data. And why would partners do that? I think in the aerospace industry, there is so much need for documentation and so much effort is spent on documenting quality data, rework that has been made on the part. And a digital twin may really help here to reduce the effort that goes into this. And that could be an incentive for manufacturers to store data in a digital twin and possibly in a digital product passport.
Thank you very much. I think that as of now, we don't have further question. I will just share my... Yes, Vasilis.
Yes, hello everyone. I'm the Dissemination Communication Manager of GENEX. Just a small addition to Carlos' presentation. As he mentioned in the introduction of his presentation, GENEX project has entered its final stage. So it will celebrate its 2-day final event on February. It will be hosted by Ita, the coordinator of the project, and it will take place in Zaragoza. Spain. For more details, I will leave in the chat the link leading to the tab of GENEX's website with more info and detail about the final event. Thank you.
Thank you, Vasilis, for mentioning this. I think it's a good segue to say that you can follow all our projects through LinkedIn or the social channels. Also, if you have marked the box while you were subscribing to this event, you will receive you will subscribe to our newsletters. They are project newsletters, so don't expect spam every other day. It's going to be either every other month or every 6 months. So it's just going to be an update on the status of our projects. And of course, you are going to receive the link for the registration or for the recording of this session. I would like to thank all of you for participating. I hope this is the first installment of a successful series, and I hope that we will have the possibility in the future to have other projects joining us. I think it was very interesting, and maybe we will adapt the time for next time, because there are always many things to be shared during this type of session. I want to thank all the speakers for attending and preparing their presentation and for being very attentive with timing. And I want to thank Vasilis for preparing the graphic of the event and supporting the organization. And I want to thank Martina for supporting me in preparing everything. So I think that we are quite on time. We are perfectly on time. And I think we can close this session. And thank you all for attending, and talk to you soon, I hope.
Thank you.
Thank you. Bye.
Bye-bye.
Thank you. Goodbye.